Inverse functions. Okay, so here's two functions, f of x and g of x. Let's calculate f of 5. What would that be? You don't have this? Okay, so f of 5. If f is 3x minus 2, what do you get when you plug a 5 in there? 13. 3 times 5 is 15, minus 2 is 13. Okay, so then if I were to take that output of 13 and plug it into g, what would I get? 5. So I kind of got a round trip, right? I plugged in a 5, I got a 13, plugged 5 into f and I got a 13. I took the 13 and plugged it into g and I got 5 back. So we can kind of think of it like a round trip. If I were to compose f and g, right, put them in back-to-back function machines, we do f first, g. When I put a 5 in here, I got a 13 out. Took that 13 and plugged it into g, and I got 5 back. So what I plugged in went through f, went through g, came back out the other end. So if I did this in general, g composed with f, I actually just did f composed with g, but let's do it the way that I said. I want to find g composed with f. So that means g of f of x. So what's my formula for f of x? 3x minus 2. So I'm going to do g of 3x minus 2. Just replace f of x with its formula. And then g of 3x minus 2, so I want to plug 3x minus 2 into my g machine. So I'm going to replace all the x's in g with 3x minus 2's. So instead of x plus 2, it's going to be 3x minus 2 plus 2. And then all over 3. And when I simplify this, following the order of operations, the minus 2 and the plus 2 cancel, and I get 3x over 3, which is x. So x went in, my input was x, x comes out, output is x. So if I were to do it with the function machine, the two function machines, I'd have f first, oops, then g. If I plug an x into the f machine, I get 3x minus 2. Plug that into g, and we get x back out. So what went in came out in the round trip. So two functions that have this relationship where when you compose them, whatever you put in is what comes out, those are called inverse functions. They basically undo each other, right? Whatever f did, g undoes and gives you your input back. Okay, so you put an input into f, it does some stuff to it, you get an output, you take that output and put it into g, and g undoes everything that f did, so that you get your x back. If I do g, f composed with g, do the function machine or in the opposite order. So this time g comes first. If I put an x into the g machine, what do I get out? X plus 2 over 3. Then I'm going to take that and put it into f. So I'll do that over on the side here. So I have to do f of x plus 2 over 3. So that means in my f formula, I'm going to replace all the x's with x plus 2 over 3's. So I'm going to have 3 Instead of multiplying by x, I multiply by x plus 2 over 3 minus 2. When I simplify, these 3's cancel. I get x plus 2 minus 2, which is x. So when I plug x into G, out comes x plus 2 over 3. When I put that into F, turns it back into x for me. So if I compose them in either direction, they undo each other. F undoes all the work that G did. G undoes all the work that F does. So these two functions reverse each other, right? Maybe if I write them down again, remember f of x was 3x minus 2, and g of x has to undo what f did. So f multiplies by 3 and then subtracts 2. How would you undo this? What would you do first to undo multiply by 3, subtract 2? Add 2. That undoes the subtraction. Oh, I just gave it away. And then to undo the multiplication, divide by 3. That's the formula for g of x. It undoes what f did. F multiplied by 3 and then subtracted 2. To undo it, you undo the steps that f did in reverse order. So these two functions we call inverses. They undo each other. Okay. So when we compose them, if two functions are inverses, that means that when you compose them, you always get x. Now we have a little new notation here. If g is the inverse function of f, we write g equals f, and it looks like to the exponent of -1, but it does not mean that. We're repurposing an old notation to mean something new. When you see f looks like raised to the power of -1, you would just read that f inverse. That just means the function that is the inverse of f. Okay, so it does not mean f raised to the -1, which would be 1 over f of x. So what's the inverse of putting on your socks and then putting on your shoes? Take off your shoes, take off your socks, right? Inverse functions undo each other. Okay, so if you put on your socks and then put on your shoes, to undo it, you have to undo it in the reverse order that you did it. So you have to remove shoes, then remove socks. Undo each move you did in the reverse order of how you did it the first time. Same thing with math. Look at what you did, undo it in the reverse order that you did it. So how would you find the inverse of adding 3 to x and then multiplying the result by 6? Divide by 6. So the last thing I did was multiply by 6. So the first thing to undo should be to divide by 6. Then subtract 3 from x. Then subtract 3 from x. Well, I'll just say then subtract 3 from whatever you got after you divided by 6. So if we added 3, then multiplied by 6, we should divide by 6, then subtract 3. That would undo what I did. All right, so if I want to make a little table of values for f inverse, given a table for f, let's see what I can do. Okay, so let's keep the idea of round trip in your head. Okay, when I compose these two, I get a round trip. So if I plug x into the f machine, I get 2. So if I put 2 into the f inverse machine, what should I get? 1, because you get a round trip. So if 1 is the input to f and you get an output of 2, then when you plug a 2 into F inverse, you should get the 1 back. And if when you put a 2 into the F machine, you get 5, then when you take that 5 and put it into the inverse machine, you get 2 back. So then 3 goes into F and you get 7. Take that 7 and plug it into F inverse, you get 3. So then 4, 4, and 1, 5. So if you know points on F, what can you say about the points on F inverse? They are what? So let me say it differently. 1, 2 is a point on F. If you know 1, 2 is a point on F, what point has to be on the function F inverse? 2, 1, input of 2, output of 1. Okay. That means that the point 2, 1 is on F inverse. So F and F inverse swap inputs and outputs. The inputs of F are the outputs of F inverse. The outputs of F are the inputs of F inverse. This is just a consequence of the round trip idea. You put something into F, you get an output. That output becomes an input to F inverse, and the output of F inverse was the original input to F. So all your X's and Y's trade places when you have two functions that are inverses. Inverse functions just swap the input and the output. That's what an inverse function does. So that means that the domain of F is the range of F inverse, because domain is the set of all inputs for a function. So if you take all the inputs of F in a set, that's what you're going to get as outputs for F inverse. And vice versa. The range of F is the domain of F inverse. All the outputs of F are what you put in as inputs into F inverse. So not all functions have an inverse function. For example, here's the graph of f of x equals the absolute value of x. So I'm just going to fill out a few values for f. So when x is -2, what's f of x? 2. So I get 2, 1, 0, 1, 2. Get a few outputs. So if I wanted to make a table of values for the inverse, I would use my round trip idea, or I could just swap inputs and outputs. So if -2 is my input into f, then when I take that value of the output and plug it in to F inverse, what should I get out? -2, right? So this would be 1, -1, 0, 0, 1, 1, 2, 2. What is the problem with that table of values? It doesn't? Oh, well, that's okay. That's okay, because this should be a different function, right? In fact, all the inputs and outputs are reversed. So when you graph the inverse function, it's not going to look the same as the original function. There's a different problem.
The same numbers.
What do you mean they're the same numbers? Okay, so my x, in my x row here, I have a 2 written down twice, right here and right here. What's the problem with that? Is there a problem with that?
You're saying 2 is
Yes. I have 2 different outputs for the input of 2, right? When 2 gets input here, my output's -2. And then a little while later, I put in 2 as my input again, and this time my output is +2. When you have when you have the same input that produces two different outputs, that's not a function. So what I'm calling f inverse here is not a function. We could tell if we plotted these points. If I plotted 2, -2, 2, -2, 1, -1, 0, 0, 1, 1, 2, 2. When I plot it, that green graph is the graph of f inverse, these points I drew. It doesn't pass the vertical line test, so it's not a function. So not all functions have an inverse function. So this is kind of a subtle thing. All functions have an inverse, right? I just graphed it. It has an inverse. It's just that that inverse isn't a function itself. And those are the only kinds of inverses we're actually going to study. We only are interested in the inverse if it is itself a function. Okay? Because functions are what we are comfortable studying in this class. Okay, so if the inverse isn't a function, sometimes we just are lazy and we say it doesn't have an inverse, right? It does, it's just that it's not the kind of inverse we want, okay? So graphically, we just showed what the problem was. The inverse function, right? That's not really a function, didn't pass the vertical line test. So we could have used the horizontal line test first, right? So the horizontal line test helps us decide if a function has an inverse. So it says if every horizontal line intersects the graph of f at most once, then it has an inverse. If it ever intersects twice, no inverse. So this way I wouldn't have had to do all the work of getting a table of value, plotting the points, and looking at the result. I could look at the original function, draw a horizontal line, see, oh, it crosses in two places. This graph does not have an inverse function. Its inverse will not be a function. So we have quick shortcut. Vertical line test tells you if the graph is itself a function. Horizontal line test tells you if its inverse is a function. Has to pass both to have an inverse. So if I was going to draw a function that's everywhere increasing, so meaning when you read it from left to right, it's always going uphill. So it could look like this. Could have peaks, right? No peaks, but it always is going up. Sometimes slow, sometimes fast, but always increasing. Okay. What can you say about this? Is it a function? What I've drawn here. Yep, passes the vertical line test. Does it have an inverse function? Yep, it's also going to pass the horizontal line test. So this passes both BLT, which means it's a function, and HLT, which means its inverse is also a function. So we could conclude that any function that's always increasing has an inverse. Has an inverse that is also a function. So that's the conclusion. Any function that is increasing everywhere has an inverse function. So functions that have an inverse function, functions whose inverses are also functions, we put in a special class of function, categorize it in a special way, give it a special name. It's called a one-to-one function. So a function that has an inverse function is called one-to-one because for each input there's exactly one output, and for each output there was exactly one input. So the inputs and outputs correspond in a one-to-one fashion. So when I look at the absolute value function, here's my problem. Okay. It is a function because each input has exactly one output, but it's not one-to-one because I have one output that came from two different inputs. So one-to-one means each x corresponds to exactly one y, and each y was produced by exactly one x. Okay, so part of where inverse functions are so valuable is when we use functions to represent real-world things. So we'll do one example of these, and then we'll pick it up here next class. All right, so if P equals F of T gives the population of Greenfield as a function of time, measured in years since 1900, let's see what the inputs, outputs, and the units are. So my inputs into the regular old function f, not talking about inverses yet. What do the inputs look like? Which variable, t or p, is the input? T, yeah. So my inputs are t values, and the units are years since 1900. The input is t. What's the output? For the function f, the output is population size. So the output is p in number of people, right? So my input is a year. My output is the number of people in Greenfield in that year. So if I write the sentence, F inverse of 1400 equals 57, this 1400 is an input into F inverse, right? It's in parentheses, which makes it an input. But it's being inputted into the inverse function, which means it was an output from F, right? Because inverse functions swap the role of input and output. So 1400 is an input for F inverse, which means it's an output for F, which means that 1400 represents what? Population of Greenfield. So 1400 people in Greenfield. Okay. And the 57 being an output of F inverse means it was an input for F. So that 57 represents what? 57 years since 1900. So we would say in 1957. So that sentence says that F inverse of 1400 equals 57. It means there were 1400 people in Greenfield in 1957. Yeah. Yeah. Yeah, so we are making an assumption here that this is a one-to-one function. Not a very safe assumption. Yeah, because populations can go up and come down. And if it ever went up and came down, then there'd be two of the same population for different years. So we are making a pretty unsafe assumption here. Good observation. All right, so the inverse function in general tells you the year in which the population was a certain size. So F inverse tells you a year for a given population size. So it takes population size as its input and outputs the assumingly only year that that population occurred. All right, so before you go, just work on this part B on in your groups. And when you finish, or it turns, oh, actually we go till 7:20, right? Okay, yeah, do this one. I was thinking 7:15 for some reason.